All right, in this video, we're going to go through some more optimization example problems. So in this example, we have an open top rectangular box constructed from a 10 inches by 16 inches piece of cardboard by cutting congruent squares from the corners and folding up the sides. So basically what ends up happening is you're looking for, usually I show a visual of this in class, but you're going to end up with a box, whoops, that looks like this. And it's open in the top, and basically how you got there was you started out with a piece of cardboard that when you cut out the corners of it, so then you pretend like those corners are gone now, what you can do is you can take this this piece and you fold it up, so that way it goes from being where it was flat on the desk, and then you fold it up so that it becomes right here. Okay, so that's just visually how they're doing this, and it's just important to know what the first piece looks like. Whoops. Before you start trying to calculate everything. So an open top is constructed from 10 inches by 16 inches piece of cardboard. So this originally was 16 inches here and 10 inches here. And then cutting congruent squares from the corners and folding up the sides. And we want to find the dimensions of the box with the largest volume. So one thing that we have to mention is this whole piece of cardboard was 16 by 10, but I'm cutting out these pieces. And these are squares, so I know that all of the cuts I'm making are the same. So I'm going to call all of those cuts X. I don't know how big I'm cutting them, but awesome. So that if it was folded up, this would have a height of X, essentially, is what's happening. Okay. And so if I'm going to try to, so I drew my picture, one, identify my variables, two. I'm trying to find the dimensions of the box with the largest volume. So I'm trying to maximize the volume of your box. Oops. So I guess I can just write V. And so then let's write an equation for our volume. Now, we just talked about, I can see it better in this 3D version, I think. So this length was 16 before I cut out these corners. So the length of my box now, I've cut away this piece and this piece, so it's actually only going to be this long. And so how to get that length is to take the full 16, and then you cut out two x's. So the length of that dimension of that box now will be 16 minus 2x. And then same way with your 10-inch piece side, 10-inch side piece. You have 10 inches, and then I cut out x's, so then the length of it this way would be 10 minus 2x. And then we just talked about previously that your height would be x. So if I was going to maximize my volume, I'd have to multiply all those three things together. So it'd be 16 minus 2x times 10 minus 2x times x. Some constraints that I have here, it doesn't give me any more information. Oops, step 3. It doesn't give me any more information in the problem. The only thing I know is that x has to be positive. And that's okay that it didn't give me any more information, because my equation that I'm trying to maximize actually already only has one variable, so I don't have to bother trying to rewrite this in terms of like x's and y's and then do some substitution. I can just right away simplify our volume formula, and then I'll take the derivative of it. So let's simplify it first. So another way to rewrite this would have been volume equals, all right, let's FOIL. So then I get 160, let's see, minus 32x minus 20x plus 4x squared. And then I still have that x on the outside, so then I can distribute that in. And then these can combine too. That would have been negative 52x, right? Oops. Okay, so then and then once I distribute this x into each of those three pieces, I'll have 160x minus 52x squared plus 4x cubed. Okay, so then now I can start applying my first derivative test. So I'm going to take the derivative of volume, and I'll get 160 minus, what would that be? 104x plus 12x squared. And then I set it equal to 0, and then I think I can pull out a GCF of 12, maybe. I don't think 104 is divisible by 12. Nope. Let's see. So it looks like my GCF is 4. So I'm going to pull out 4. Then I'm also going to rewrite them in order because it's driving me crazy. We got 3x squared. So then minus 26x, and then 160 divided by 4 is plus 40. There we go. And then we're going to use reverse box method to actually factor this. And if you do that, you'll end up with 3x minus 20 and x minus 2. And so then from there, we can go ahead and we can start finding our solutions. So then you can, 4 will never equal 0, but you can set 3x minus 20 equal to 0, and then x minus 2 equal to 0. So I'll get x equals 20/3 and x equals 2. And this is our first example where we have two answers, so we definitely need that sign chart to figure out maximum and minimum pieces. So if I do that, we'll do 2, we'll do 20/3. We'll do our first derivative test. So if I plug in 0, for example, if I plug 0 in here, let's use a different color. If I plug 0 into here, I'd end up with a positive number times a negative number times a negative number. So this would be positive. And then if I plug in, let's see, 3, I'd have a positive number times a negative number times a positive number. So that'd end up being negative. And then if I plug in 10, 10 would have a positive number times a positive number times a positive number. So then those would all be positive. All right, so then looking at our options here, I want to maximize volume. And so between 2 and 20/3, 2 looks like a local maximum, whereas 20/3 looks like a local minimum. So we're going to go with 2, actually, as our x coordinate. Now, we don't want to find just x, right? X equals 2. What you actually want to find are the dimensions of the box with the largest volume. So I'm going to go ahead and I can plug in my x value here to figure out my actual dimensions. So 16 minus 4 would be an 8 inches box. Nope. 12 inches box by 10 minus 4 would be 6 inches by 2 inches. So if I have this would be the dimensions of the box with the largest volume. So it would be a 12-inch by a 6-inch by a 2-inch box, and that would have the maximum volume. Awesome. All right, let's go ahead and go to the next example. So a printer needs to make a poster that will have a total area of 200 inches squared and will have 1-inch margins on the sides, a 2-inch margin on the top, and a 1.5-inch margin on the bottom. What dimensions of the poster will give the largest printed area? So let's go ahead. We'll draw our poster, and then it needs some margins, so we're going to write those. 1-inch margins on the sides, so that's 1 inch. That's 1 inch. A 2-inch margin on the top. So that length right there is 2. And then a 1.5-inch margin on the bottom. Awesome. What dimensions of the poster will give the largest printed area? So we've gone ahead and we've drawn our picture. And so we're trying to figure out from there. Now we got to label our variables. So let's call this side length of your poster, we can call it X. And then this one's Y. And we want to, so there's step 2, identify your variables. And then in step 3, we want to go ahead and identify what we're trying to maximize or minimize. So we're trying to maximize the printed area of the poster. So I'm just going to call it A for area. And so the printed area is this part in the middle where I don't take up any space in the margins. So to find area, you have to multiply this side by this side, but I have to take into consideration the margin. So actually the length of the bottom on the printed area would be the whole sheet, so X, and then you have to subtract the margins from it. And so each of these margins is the length of 1. So my first side would be X minus 2, because it's the whole length of the poster, and then minus 1 inch on each side, so minus 2. And then my my side length for the height of the poster is my Y, Then I have to subtract those margins from it as well, because then that'll produce just the printed area. So y minus 3.5. All right, let's talk about some of our constraint pieces. So constraints. Obviously, x and y have to be positive, and then also it gives us one more piece of information in the problem. The poster has a total area of 200 inches squared, so that means that when you just do x times y without the margins, like the actual piece of paper, you get 200. And so this is what we're going to use to rewrite our optimization equation in just one variable. So I'm going to go ahead and divide, I don't care, let's divide by x. Okay, so then we have y equals 200 over x. And so now I'm going to use that to plug in, oops, I think I used red previously. I'm going to use that, and I'm going to plug it in for y here. So then I'll end up with the equation y equals, nope, a equals, excuse me, x minus 2 times 200 over x minus 3.5. And then here you have a couple of options. I'm actually going to rewrite this first by foiling it before I try to take the derivative. You could take the derivative by using product rule as well. So we'll get x times 200 over x would just give me 200. X times negative 3.5 would give me negative 3.5x. Negative 2 times 200 over x would give me negative 400 over x. And negative 2 times negative 3.5 would give me negative 7. All right, so then now, step 5, I'm going to go ahead and take my derivative. So my 200 and my 7 go away. My derivative of negative 3.5x is just negative 3.5. And then my derivative of this, let's see, it would have originally been written negative 400 x to the negative 1. So plus 400 x to the negative 2, or as x squared on the bottom. Set that equal to 0. And then let's see, we can multiply or move over the 3.5 first, and then multiply by x squared, divide by 3.5. Oh, what's that? Oh, that is not a nice number. It looks like we get 114.286. Square root both sides. Oops. And we end up with, oh, let's see, x equals 10.690. Okay, so it's all right that it's not a nice number. This is a more realistic mathematical situation, so your numbers don't have to be nice necessarily. And we are going to go ahead and then do our sign chart just to double check. Just do a little mini sign chart over here. Usually if you only have one answer, that means it's going to be your answer. So let's see, if I plug in 1 into my first derivative, I'd end up with a positive number. If I plug 12,000 into my first derivative, this would be a really small fraction. So a negative number plus a really small fraction would be a negative number. So this is in fact a maximum, or this would produce a maximum largest printed area. And so then the last step that we have to do is we have to take this x value and use my constraint formula to solve for what my y value would be, because they want to know what are the dimensions of the poster that will give the largest printed area. So then I can plug it in. So I'll have y equals 200 divided by 10.690, which gives me, let's see, 18.708. And so then those would actually just be the dimensions, of your poster, right? The x would be, this would be a 10.690 inch by 18, oops, 0.708 inches. My dimensions are a little bit off, but that's all right. That would give you the maximum Largest printed area.